Hi everyone, welcome to Go Classes. Please tell me, is the audio video clear? Am I audible? Please let me know. Is everything clear? Audio video. So let's start now. Please let me know. Is everything clear? Audio video. Let me know. Is everything fine? Okay, so let's start. So we were discussing All India Mock Test 1 solutions. Now this is the part 3. Okay, in this part we will see the remaining questions of All India Mock Test 1. This link of All India Mock Test 1 you can find in the description if you want to attempt. If you did not attempt this All India Mock Test for GATE Computer Science 2024, then you can find the link in the description and you can attempt this test. Okay. So let's start now. Let me introduce myself. My name is Deepak Punia. I have completed my MTech from IISc Bangalore. Also, multiple times I have secured top rank in the GATE exam like All India rank 53, 67, 107, okay, 206, 256. So multiple times I have secured top rank in the GATE exam. Okay, now let's start. So if you want to enroll for the test series of Go Classes and GATE Overflow, you can do that. Okay, just go to this website. Okay, so the link you can find in the description. So basically, if you want to enroll for the GATE Overflow plus Go Classes test series, then you can go to this link and you can join the test series. Okay, in this test series, let me tell you, there are more than 100 tests and there are 20 mock tests. There are 20 full length mock tests are there. So you can subscribe, you can enroll for the Go Classes and GATE Overflow test series by going to this link. This link you can find in the description. Also, if you want only the mock test, that also you can do. Okay, if you want to subscribe only for the mock test, all 20 mock test, if you want to subscribe, that also you can do. Okay, basically just go to this website. So here you will see this option, you will see GATE Overflow Go Classes full length mock test. Okay, so you can see this is the mock test package. This is the mock test package. So in this package, basically, if you enroll for this package, then you will get all 20 mock tests you will get. There are total 20 mock tests in the GATE Overflow plus Go Classes test series. All those 20 mock tests you will get, okay, if you enroll for this mock test package. So if you don't want to enroll for the entire test series, you only want the mock test of Go Classes and GATE Overflow, then you can enroll for this package. Okay. Also, let me tell you that discrete mathematics and engineering mathematics, these complete courses are freely available on the Go Classes website, also on the app. So you can go to Go Classes website or you can go to the app. So you can go to Go Classes app on Android, also on iOS. You can find Go Classes app, you can find. Okay, so you can go to the Go Classes app or website and you can learn these two courses, complete discrete mathematics, also complete engineering mathematics. These two courses are freely available. These are free for all learners on the Go Classes website, also on the app. Okay, so you can enroll and you can start your preparation. Okay, you can join Go Classes Telegram group. So this is the username for the Go Classes Telegram group for doubt discussions. Okay, if you have any doubts related to GATE Computer Science preparation, technical or non-technical doubts, if you have, then you can join Go Classes doubt discussion Telegram group. You can join. This is the username of the Telegram group. Again, the link you can find in the description. Okay. So let's start now. Also, one more thing. If you are a GATE 2025 or 2026 aspirant, if you are preparing for GATE 2025 or GATE 2026, then you can enroll for GATE Go Classes GATE Computer Science complete course. Okay, so again the link is in the description. You can check it out, or you can go to the Go Classes website. Go to the Go Classes website. You can enroll for Go Classes GATE Computer Science complete course. You can enroll for this course if you are a GATE 2025 or 2026 aspirant. If you enroll for this course, you will get 2 months of extra validity. Okay, if you enroll today, then you will get 2 months of extra validity. Basically, your validity will be 1 year plus 2 months extra validity you will get. Okay, so you can enroll for GATE Computer Science complete course if you are a GATE Computer Science aspirant for 2025 or 2026. Okay. Now let's start our session. So now let's study. Now let's solve the digital logic questions of AIMT 1 in All India Mock Test 1. The digital logic questions. Let's start. Let's solve this question from digital logic. The following circuit using a 3 to 8 binary decoder and an OR gate is an implementation of the function. So this circuit is given to you. In this circuit you can see there is a decoder here. This is a 3 by 8 decoder and there is a OR gate here. The question is asking what is the function implemented by this circuit. What is the function implemented? These options are given to you. You can see F, W1, W2, W3. So what is the function that is implemented by this circuit? This is what the question is asking. So let's solve it. You can see this circuit. In this circuit, this function we want to find out what is the function that is implemented. W1, W2, W3. What is the function implemented? These are the inputs, remember? These are the inputs. W1, W2, W3. These are the inputs. You can see these are the inputs. Okay. So in all the options you can notice W1 is the MSB, right? In all the options you can easily notice that W1 that is the MSB. So W1 is the MSB. So we are writing this W1 here because W1 is the MSB. Okay. Now let's solve it. So what will be the function? There is a OR gate here. So when this function will be 1, just think about it. When this function will be 1, you can easily notice that this function is going to be 1. When this function will be 1. For example, if I put all the inputs 0, 0, 0, because this is a 3 by 8 decoder, right? This is a 3 by 8 decoder. This is a decoder. So if your input is 0, 0, 0, W3 0, W2 0, W1 0, remember W1 is the MSB. So if your input is 0, 0, 0, okay, actually what is the MSB of decoder? See, you can see this is the MSB of the decoder. So W1 is connected to the MSB of the decoder. So please understand that this is MSB of the function also. This W1 is the MSB of the function also. And remember, this W1 is connected to MSB of the decoder also. So here you notice one thing, that this actually indicates simply MSB of the MSB input line. Okay, this simply indicates MSB input line. Okay, this simply indicates MSB input line. So remember, in the decoder, this is the LSB input line. In the decoder, this is the LSB input line, and this W2 is the MSB input line. So here you can notice this W1 is connected to MSB input line of the decoder. So this indicates, you can see this W2, this indicates MSB input line of decoder. Okay, so please make this observation that inside this decoder, look at this decoder. In this decoder, these are not same as these. Okay, if you don't want to confuse, then just remove these. Okay, just remove them, and you can write them. Maybe you can write them something like x0. Okay, you can just simply write them 0, 1, 2. Is this clear? You can simply write them 0, 1, 2 if you don't want to confuse yourself. Remember, these are the inputs of the function. Please understand, these are the inputs of circuit, or I can say these are the inputs of a function that is implemented. These are the inputs of function f. And remember one thing, that these 0, 1, 2, these are written inside the decoder. This is your decoder, right? In this decoder, these 0, 1, 2 are written. So remember, this 0 means this is the LSB line of decoder. This is the LSB input, or I can say this is the LSB input of decoder or LSB line of decoder. Okay, so you can see that your input W3 that is connected to LSB line of decoder, and your input W1 that is connected to MSB line of the decoder. Okay, so don't confuse these. What I'm trying to tell you, these inside you have W0, W1, W2. Inside these you have, okay, these are just notations. these are just notations. If you don't want to confuse, remember, inside the decoder, these are just notations. These are not the inputs. These are just notations. Like this y0, y1, y2. These are notations. For example, you can write them simply 0, 1, 2, 3 and so on. Okay, you don't need to write y0. This is just a notation. You can write it 0, you can write it 1, you can write it 2, you can write it 3. Okay, so very simple point. Inside the decoder, this is just a block diagram of the decoder. So please understand, this is just the block diagram of the decoder. This is a block diagram of decoder. Okay, this is just a block diagram of the decoder. Is this clear? So remember, so don't confuse this block diagram. Don't confuse this block diagram with the actual inputs. Your actual inputs are, these are the actual inputs. Okay, these are the actual inputs. Anyway, now you can easily see that your W1, that is actually connected to the MSB line of the decoder. So you can see your W1, that is basically the MSB, and your W3, that is basically the LSB. Now, if these W1, W2, W3, these are your actual inputs. If these are 0, 0, 0, if you put them 0, 0, 0, what will be the function value? If these are 0, 0, 0, then this line will be activated, right? Okay, in this situation, if the inputs are 0, 0, 0, then this line will be activated in this decoder. This line will be activated, this line will become 1. Now you can see, this line is input of the OR gate. This is your OR gate. So this line is the input of the OR gate. So your function will become 1. So in this situation, you can see your function will become 1. Okay. What about this situation? 0, 0, 1. If your input is 0, 0, 1, now what will happen? Now you can easily see, if you put 0, 0, 1 on the input 0, 0, 1, then this line will be activated. And you can see this line is also input to the OR gate. So you can easily see, I'm telling you that if you make it, okay, this like this W1, W2, W3, if you make it 0, 0, 1, okay, then what will happen? In this situation, this Y1 will be activated. Okay, this line will be activated. Basically, this will become 1. This line will become 1. All the other lines will become 0. All the other lines will become 0. You can see this line is actually input to the OR gate. This line, you can see this line, this output line, this Y1, this output is input to the OR gate. This is your OR gate. So your function value will become 1. Okay, in this situation. So this is what we are saying, that your function value will again become 1. Very simple. Now you can easily find for the remaining, when your function value will become 1, you can see to this OR gate, which lines are connected to the OR gate. I can say which output lines of the decoder are input to the OR gate. In this decoder, which output lines are input to the OR gate. So you can see this Y0, Y1, similarly Y3, similarly Y4, also Y6. These are the input to the OR gate. Yes or no? So you can easily see that your function value, that will be like this. Like for this combination, function value will be 0, because you can see in this decoder, just notice this decoder. In this decoder, which output lines are input to the OR gate? Just focus on that. So you can see this Y0, Y1, Y3, Y4, Y6. These output lines of the decoder, these are input to the OR gate. So you can see whenever they will be activated, whenever Y0 or Y1 or Y3 or Y4 or Y6, whenever they will be activated, whenever they will be 1, then your function output will become 1. Okay, so you can easily see, if your input is this, then Y0 output line will be activated. In this situation, Y0 output line will be activated. But you can see that this Y0 output line, this is not input to the OR gate. Okay, so that is the reason this function value will become 0. Okay, for this function value will become 1. Okay, similarly you can see for the remaining ones. Let me quickly write it. You can easily see that when the function value will become 1, so you can see Y4, Y6. Okay, Y4, also Y6. Here the function value will become 1. Okay, so for the remaining, the function value will be 0. So this is the simple idea. Okay, I hope you understood. Now the question is asking, what is this function? So let's find out what will be the function. So let's write the function now. The function W1, W2, W3. You can write it as summation of minterms. Yes or no? you can write it as summation of minterms where function value is 1. Where function value is 1. So basically write those minterms where function value is 1. Okay, so you can see these are the minterms where function value is 1. So you can easily see your answer will be this function we can write as a summation of minterms. I am writing the minterms here. Here I am writing the minterms for which function value will be 1. For which function value will be 1. Okay, so these minterms I can write here. So this function you can represent as summation of those minterms where function value is 1. So those minterms are basically 0, 1, then 3, 4, and then 6. Okay, so these are the minterms for which the function value is 1. Similarly, the same function you can write as product of max terms. You can write as product of max terms. Okay, here I will write those max terms where the function value is 0. So this function you can represent as a product of max terms for which the function value is 0. So what are the max terms for which function value is 0? For which the function value is 0. So you can easily see your function value is 0 for this max term, for this max term, and for this max term. So this is your answer. Okay, very simple. So these two are the answers. So your answer will be 0, 1, 3, 4, 6. Okay, let's match the options. 0, 1, 3, 4, 6. So yes, option A will be the answer. Also you can notice that yeah, no other option will be the answer. Correct. Okay, so 0, 1. Sorry, option A will not be the answer. Option A will not be the answer. Actually your answer will be F is equal to summation of minterms 0, 1, 3, 4, 6. Okay, 3, 4, 6. 0, 1, 3, 4, 6, right? Let me see the diagram again. 7 is also there. Okay. Actually 7 is also there. 7 is also there. Sorry for that. So 7 is also there. 7 will also be there. So yes, your answer will be 7 is also there. So your answer is going to be this. Okay. Because you can easily see that, look at this. 7 is also connected to the OR gate. 7, 6, 4, 3, this and this. These are actually connected to the OR gate. So that is the reason I can say your function, that is summation of minterms where function value is 1. So that will be your 0, 1, 3, 4 and then 6, 7. This will be your answer. Answer will be option A. Okay. Is this clear? Very simple. So for this question, the answer will be option A. Okay. So let me just correct it, that when the input is 1, 1, 1, then also function value is 1. Okay. So your 2,5, pi 2,5. So yes. So the answer is going to be only option A. For this question, I can say answer option A. Okay. So let's move on now. Anyway, this is a very simple question. Let's see this question. So let's see this next digital logic question. Suppose that n is a 5-bit 2's complement number. M is its additive inverse. Okay, what is n? N is basically 5-bit 2's complement number. Okay, 2's complement number. And what is m? M is its 5-bit additive inverse. Additive inverse. Okay, additive inverse. Note that n cannot be 1, 0, 0, 0, 0. That means minus 16 in the decimal, because n is basically 2's complement number. N is 5-bit 2's complement number. So n cannot be minus 16, because what is the additive inverse of 16? What is the additive inverse of minus 16? That is plus 16. So you can see plus 16 you cannot represent using 5 bits in the 2's complement notation. Okay, so that is the reason n cannot be minus 16. Okay, n cannot be minus 16 because the additive inverse of minus 16, that is plus 16. Okay, and you can see that plus 16 cannot be represented using 5 bits in the 2's complement. Okay, also assume that n is not 0, 0, 0, 0. This is also given to you. If we reinterpret, the question is saying, if we reinterpret their bit patterns as 5-bit unsigned number, add them, then we add them m plus n. Keep any carry out of the leftmost place. Okay, we keep it. We don't discard it. We keep it. what number unsigned do we get in the decimal? So this is a very simple question. What is n? N is basically, this is a 5-bit number in 2's complement. This is a 5-bit number in 2's complement. Okay. And what is m? M is the additive inverse of n. Additive inverse of n. First of all, what additive inverse means? For example, this is very simple. If your n is, let's assume minus 8, then the additive inverse will be what? Then in this situation, the additive inverse will be plus 8. If your n is, let's assume 1, then your m will be basically minus 1. Okay, so this is the definition of additive inverse. Very simple. Okay, whatever number you take, if n is 0, then m is also 0. Okay, so this is the simple idea. If n is, let's assume minus 2, then m will be plus 2. Okay, so this is the definition of additive inverse. Now m is basically additive inverse of n, again in 2's complement. Okay, again this is also in 2's complement. So you can see here, okay, m is 5-bit additive inverse, that is also in the 2's complement, right? Okay, so now what we need to do? We need to do m plus n. This is what we need to do. We need to do m plus n. And the question is asking what will be m plus n? Very simple. What will be m plus n? So let's take some example. For example, consider this n equal to minus 8. Okay, let me consider n equal to minus 8. So in 5 bits, what this will be? In 5 bits, if I take n equal to minus 8, in 5 bits, what this will be? In 5 bits, this will be 11000. Okay, because this is your minus 8, right? Okay, so you can see in the 2's complement, remember, everything is in the 2's complement. So this n, this is in the 2's complement. So n will be this. Now, what will be m? M will be plus 8. Okay, in the 2's complement, what will be m? In the 2's complement, what will be m? The m will be basically like this. Now just do the addition. What the question is saying, you do the addition. Remember, the question is saying that you reinterpret their bit patterns as 5-bit unsigned number. Okay, you reinterpret m comma n as 5-bit unsigned number, then you add them and you keep any carry out of the LHS. Means you don't discard the carry. The carry you don't discard, you keep it. Then finally, the result. What is the result? If you interpret the result as unsigned, what number you will get? What result you will get if you interpret that as unsigned? And the final answer you have to put in the decimal. Okay, so let's do the addition. So here you can see this will be 0, 0, 0. 1 plus 1, that will be 0. There will be a carry 1. 1 plus 1, that will be 0 and carry 1. Don't discard the carry. The question is saying don't discard the carry. Okay, keep the carry. The question is saying keep the carry out of LHS. You can see here, keep the carry out of LHS. So don't discard the carry out of LHS. Keep it. Okay, so here what will happen now? What is this result in unsigned? If you interpret this as unsigned, then what will be this value in the decimal? What will be this value in the decimal? If you think of this as unsigned, then in the decimal, what is this value? You can see this is a 32. Okay, this value is a 32. So very easily you can see that answer is going to be 32. So this question is actually very simple. But there is one thing very interesting in this question. What is that? Can you tell me? Can you tell me what is very interesting thing here? See, the interesting thing is you can take any 5-bit number and again you will get the same result. Okay, this is the interesting thing here. What is the, see what I'm telling you, basically this n, you can take any 5-bit, 2's complement number. Okay, you can take any 5-bit 2's complement number, you can take any non-zero. Okay, you must take non-zero, any non-zero, because the question is saying n is non-zero, right? Okay, so what you can do, this n, this is a non-zero, 5-bit 2's complement number. Okay, the question is already saying that n is not 0. In the question it is already given that n is not 0. You can see. Okay, assume that n is not 0. Okay, in this question you can notice that n is not 0. So what I'm saying that you can take any 5-bit non-zero 2's complement number, you can take whatever you take, okay, and you take this m, this is the additive inverse of n, this is the additive inverse of n, okay. If you add them, m plus n, if you add them, the result is always going to be 32. The result will always be 32. This is the interesting thing here, okay. You can try this. For example, let me take this n equal to, in the last example I have taken n equal to -8, okay. Let me take n equal to some other value, maybe +4. Let me take +4. What is +4 in 5-bit 2's complement? The +4 is going to be 0 0 0 1 0 0. This is +4. What will be m? M will be -4. In 2's complement, what is -4? In 2's complement, your -4, that is basically like this. Yes or no? So this is the -4 in the 2's complement. Now if you add both of them, then what you will get? You will get 0 0, 1 plus 1 0, 1, 1 plus 1 0, 1, 1 plus 1 0, 1. Again you can easily see your result is again 32. Okay, if you interpret this as unsigned, okay, if you think of this as unsigned, then again this result is 32. This is the interesting thing here. Okay, I hope you understood. So remember, this is very interesting, right? That whatever number you take, you can take any 5-bit 2's complement number. Whatever 5-bit 2's complement number you take, it should be non-zero. It should be non-zero. Any non-zero 5-bit 2's complement number you take, if you add that number with its additive inverse, means m plus n, if you do, then if you interpret the result as unsigned number, this result, if you interpret this result as unsigned number, then that unsigned number will be always 32. That will always be 32. Okay. And remember, this is the reason why this is called 2's complement. This is the reason why this is called 2's complement. Let me tell you. Let me give you the general result. Let me give you the general result. Actually, the general result is like this. You can take n bit. You can take any n bit non-zero number. Okay, this n. What you can do? You can take any non-zero. You can take any non-zero n bit number. Okay, what you can do? Let's assume this a. Let me call it a. What is a? A is any non-zero n bit number in 2's complement. N bit number in 2's complement. Okay, in 2's complement. And what is m? What is b? B is additive inverse of a. Okay, what is b? B is additive inverse of a. Okay, again in 2's complement. Again in 2's complement. Okay, so that is additive inverse of a, again in 2's complement. Now if you do a plus b, and this result if you interpret as unsigned number, okay, this result, whatever result you will get, if this result you interpret as unsigned number, if you think of this pattern, this result, if you think this result, if you think as unsigned number, then what will be the answer? Anyone? Then tell me, what will be the value? The value will always be 2 power n. The final answer will be 2 power n. So this is the general result. Okay, basically very simple point. The same thing will happen for 4-bit also. For example, you can take this n equal to 4-bit. Okay, you can take n equal to 4-bit. Like, let me take n equal to any number you give me. For example, let me take it -1. Okay, let me take it -1. So in 4-bit, what is -1? In 4-bit, what will be -1? So you can easily see your +1 in 4-bit, that will be 0 0 0 1. This is +1. So in 4-bit, this -1, this will be 1 1 1 0. Okay, this will be 1 1 1 0 in 2's complement. This -1 in 2's complement, that is 1 1 1 0. Now what you do? This is your n. Okay, if you do this m also, what will be m? M is -1. If n is -1, then m will be +1. Then m will be +1. So that is 0 0 0 1. If you add both of them, then what will happen? Then both will happen. Sorry, what will happen now? Is there any mistake here? N is -1. In 4-bit, what is -1? Did we do some mistake here? 4 bit, if you take n equal to -1, +1 is 0 0 0 1, so the -1, what is the mistake we did? Let me know. What is this one? Sorry, okay, this will be 1, right? Okay, sorry, this will be 1. Okay, so you can see this will be 1, so this is going to be -1. Yeah, this is the mistake. So you can see this will be the -1. Okay, you can see +1 is 0 0 0 1, so in the 2's complement this will be -1. Okay, in the 2's complement this is going to be the -1, and your m is +1, so that is 0 0 0 1. And finally, if you add both of them, then what you are going to get? Again you are going to get this. And if you interpret this as unsigned, if you think of this as unsigned, let me think of this as unsigned. Okay, let me calculate this as unsigned. Then what this value, can anyone tell me? Can you notice this is your 2 power 4? Yes or no? This is your 2 power 4. Okay, so this is the idea. I hope you understood. Is this clear to everyone? Okay, so let me tell you one thing, just a small point. This question is actually a standard question. This question that we have taken, right? Okay, this question that we have put in the AIMT All India Mock Test 1. So this question is actually a standard question from this university. From this, you can see Rochester University. From this university, this question is taken. Okay, this same question we have taken from this university. And you can see there is something interesting here. What is that? What is that? You can see that is the reason it is called 2's complement. You can see because of this property, we call it 2's complement. This 2's complement has this property, and because of this property we call it 2's complement. 2's complement. Okay, and what will happen if your number is 0? What will happen if your number is 0? Okay, if your n is equal to 0, then what will happen? Tell me. In this situation, your m also will be 0. If n equal to 0, then your additive inverse, that also will be 0. Okay, and if you add both of them, okay, in 5 complement, so this is your 0 0 0, m is also 0 0 0. In this situation the result will be 0 0 0. So you can see that is the reason in the question it is given that n is non-zero. Okay, so you can see if n is 0, then the result is going to be all 0. But if n is not 0, so basically it's like this. Okay, let me again tell you, this is the final conclusion. Let me give you the conclusion. Okay, this is the conclusion, remember. So let me give you the final conclusion. This is very interesting result, you can see. So the conclusion is like this. You can take a, which is any, okay, let me take any non-negative, any n bit number. Okay, let me take any n bit number, 0 or non-zero. Okay, let me take any n bit 2's complement number. 2's complement number. Let me take this a equal to any, whatever you want. Remember, any n bit 2's complement number you take. What is b? B is additive inverse of a. B is additive inverse of a. That also in 2's complement. That also in 2's complement. Okay. Now if you add them, then what will happen? Now what you do? You add both of them. You add both of them, a plus b you do. The result is r. If you think of this r as an unsigned number, then what will happen? If you think of this r as an unsigned number, then what will happen? So let me tell you, this will happen. Two cases will happen. Okay, two cases will happen. Case 1, if a 0, okay, if a 0, then remember your final answer. This your final answer, right? If you interpret this result, if you think as unsigned number, then what will be your answer? Let me call this answer as x. Let me call this answer, or maybe let me call this answer as y. So y in decimal. Okay, so tell me what will be y? If this a is 0, then this y will be 0. But the case 2, what is case 2? If a is non-zero, then what will be y? Then y will be 2 power n. Then y is going to be 2 power n. Okay, so this is an interesting question. I hope you found this interesting. And remember, this is the reason you can see a plus additive inverse of a. okay, this number a plus additive inverse of a, they are giving you 2 power n. They are giving you 2 power n. This is the property of 2's complement. This is the property of 2's complement, that if your input is in the 2's complement, if all the numbers are in 2's complement, then you can see if you add any 2's complement number to its additive inverse, then you can see the result you are getting, that is 2 power n. Okay, that is always 2 power n. You can take any n bit number, you can take any n bit 2's complement number, you can take. If you add this number to its additive inverse, then remember, always your answer will be 2 power n. So this property is there. Okay, this interesting property is there. So now let's move on. Now let's solve this question. This is very simple question. The resultant of binary subtraction, we need to do binary subtraction, we need to do. So what is the result of this binary subtraction? So let's see. The result we need to find out. 1 1 1, these are the inputs, 0 1 0 1. From this number we need to subtract 0 0 1 1 1 1 0. Okay, so you can see this binary subtraction we have to do. So let's do this. See, binary subtraction is very similar to your decimal subtraction. How do you do the decimal subtraction? For example, if I give you some number like 8 2 3 4, okay, from this number let's assume you want to subtract 7 8 7 9, then tell me what you will do in this situation. How do you do the subtraction? The decimal subtraction, the normal subtraction from your school life. How will you do this decimal subtraction? You can see there is a concept of borrow, right? You can see there is a concept of borrow. Let me make it 0. There is a concept of borrow, right? We have a concept of borrow. Okay, so you can see what you will do. From here you cannot take a borrow. Okay, in your school life you have seen this subtraction, right? So you can see from here you cannot take a borrow. So what you will do? You will do like this. From here you will take a borrow and then it will give this to it. So what this will become? Okay, this will actually become 14. Why this is becoming 14? Okay, when this borrow, see here borrow is coming. Okay, that borrow you are giving to this. So what this will become? This will actually become 4 plus 10, because 10 is the base. Because 10 is the base, right? Yes or no? This will actually become 4 plus 10, because 10 is the base. In the decimal system, the base is 10. The base is 10. So you can see this will become 14. 14 minus 9, that will be 5. Okay. Now you can see one thing. When you took the borrow, then this also became 10. 0 plus 10. Yes or no? This also became 0 plus 10, because the base was 10. What is 10? Why this 10? Because the base was 10. This was 10. Okay. So basically this became 0 plus 10. And then this has given one borrow. So this has become 9 minus 7. That is 2. Okay. Now this has become 0, because this was 1 and we have already taken the borrow. So you can see this has become 0 now. Now this has become 0. Okay. After that, this 8 will give a borrow. Now what this will become? This will become 0 plus 10. Now this has become 0 plus 10. So 10 minus 8, that is 2. And remember, finally 7 minus 7, that is 0. So like this we do the decimal subtraction. Similarly, you can do the binary subtraction here. 1 minus 0, there is no need to borrow. Just directly put it 1. 1 minus 0, there is no need to borrow. Now 0 minus 1, there is need to borrow. Yes or no? We need to borrow. So let me borrow. When I borrow, then tell me what this will become. What this will become? This will become 0 plus 2, because 2 is the base. Because now 2 is the base. The base of binary system. 2 is the base. So this has become 2. 2 minus 1, that is 1. Okay, 2 minus 1, that is 1. Now remember, this was 1, but this has given one borrow. This number has already given one borrow. So now this has become 0. Now this has become 0. Okay, now because this has become 0, so we need to take borrow again. Okay, this has become 0, so we need to take borrow again. So we will take borrow like this. Okay, we will take borrow like this. Now what will happen? Now this actually will become 0 plus 2, that is 2. Okay, because this 2 is because of base. This is the base of binary system. So you can see this will become 2 minus 1, that is 1. Okay. Now remember, when this number gave borrow to this number, when this gave borrow to this number actually became 2. This number actually became 2, right? This number actually became 2. But after that, one borrow has gone from it. So this became 1. So finally, this has become 1. 1 minus 1, that is 0. Okay, so similarly, you can easily do. Now this has become 0. So this you can take borrow from here. This will become basically 2 minus 1, that will be 1. Okay, now this has become 0. So this is 0. So this will be 1. So like this, your answer will be 1 0 1 0 1 1 1. Okay, your answer will be 1 0 1 0 1 1 1. Answer will be option B. Okay, so this is actually a very simple question, right? Okay, this is quite a simple question. 1 1 1 0 1 0 1. From this you want to subtract 0 0 1 1 1 1 0. This is what you want to do. This subtraction you want to do. So this is actually very simple. 1 minus 0, that will be 1. You need to borrow. Then 2 minus 1, that will be 1. Now this is 0. Now this is 0. So again you will borrow. So this will become 2 minus 1, that is 1. This will become 1 minus 1, that is 0. This will become 0 minus 1. So again you will borrow. And finally this will become 1. Here you will get 0. Here you will get 1. So you can see your answer will be option B. Okay, so this is quite very simple question. Now let's move on. Now let's solve this question from the digital logic, and this is also a very nice question. A circuit is already given to you. The question is saying that for the following circuit, assume that all the logic gates, these logic gates that are given to you, all the logic gates have non-zero propagation delay, equal propagation delay but non-zero, equal propagation delay but non-zero. Okay, so this is a very beautiful question. Let me solve it. You can see x comma y, they are 0 0. X comma y, they are actually 0 0. Okay, now the options are like this. Read the options. What the options are saying: which of the following is true about the output y when the z changes? When the z will change. See, this is the output y. Now x is already 0. X is already 0. Y is already 0. This is your output. Okay, if the z changes, then how the output will change? The question is asking when the z changes, when the input z changes, then how the output y will be changing, this output p will be changing. Now some options are giving. If z is changing from 1 to 0, then this p will change from 1 to 0. If z is changing from 1 to 0, then p will momentarily, for a moment, it's like a glitch. Okay, for a moment it will change from 0 to 1. It's like a glitch. When z is changing, when this input z is changing from 0 to 1, then the output p is momentarily, for a moment it is changing from 0 to 1. When the input z is changing from 0 to 1, then this output p is momentarily, for a moment it is changing from 1 to 0. So which option is correct? Okay, and remember one more thing is given, that actually this p should remain unchanged. Actually this p should remain unchanged. Now what this means? This p actually should remain unchanged. Now what that means? Let me ask you. You tell me, if there is zero propagation delay, you tell me if there is no propagation delay, then what will happen? Let me know. If there is no propagation delay, assume there is no propagation delay. In this situation, what will be the output p? If you assume there is no propagation delay, just tell me this point. Okay, just assume there is no propagation delay. If there is no propagation delay, and remember x is already 0, y is already 0, then whatever is the value of z, p must be 0 or p must be what? Just tell me. X is already 0, y is already 0. If I take z equal to 0, what will be p? Just tell me what will be p if I take z equal to 0. If I take z equal to 0, p will be 0. If I take z equal to 1, what will be p? If I take z equal to 1, then again you can notice, if I take z equal to 1, if I take, then again you can notice that this p actually will become 0. Again p will become 0. So what I am telling you? I am telling you, whatever you take, see, whatever value you take, if you have no propagation delay, if you assume there is no propagation delay, okay, if you assume that there is no propagation delay, if you assume this, then in this situation output must always remain 0. Can I say output must always remain 0? Yes or no? If you assume there is no propagation delay, then can I say output must always remain 0? Do you agree with me? Okay, very simple point. And the same thing is given in the options. the same thing is given in the options. See, whatever value of z you take, notice here, I can say whatever z you take, whatever value of z you take, what should happen? Whatever value of z you take, the output must always be 0. Whatever value of z you take, this output must always be 0, right? This is what is given here, that whatever z value you take, even though the output should remain unchanged. Yes or no? Ideally, the output should remain unchanged. Yes or no? In all the options, this is given that ideally, the output should always remain unchanged. The output should always remain 0. But, when you change the input, when this z you change, in case of propagation delay, if your propagation delay, equal value of propagation delay, yes or no? If this circuit, all the logic gates, if they have propagation delay, some propagation delay is there, some delta propagation delay is there, which is non-zero. Okay, all of them have the same propagation delay. All of them, they have the same propagation delay. This also has propagation delay delta. They have the same propagation delay, which is non-zero. In this type of situation, if you change the input z, then for a moment there will be a glitch at the output. Notice. Okay, you can see for a moment there will be a glitch at the output. So the question is asking, what is that glitch? And when that glitch will come? When the z will go from 1 to 0, or when the z will go from 0 to 1? In which situation the glitch will come? Okay, momentarily simply means glitch. Basically, a glitch will come. Okay, but when the glitch will come, and what type of glitch it will be? This glitch, it will be from 1 to 0 or 0 to 1. And when it will come when z is 0 to 1 or 1 to 0. So this is the question. Did you understand the question? This is a beautiful question. You can see all the options, everything is given to you. In options, everything is already given to you. You can see in the question, every information is given to you. This is a beautiful question. Now let's solve it. So this type of question, you can easily solve using timing diagram. See, whenever your propagation delay question, the best way is timing diagram. Yes or no? Whenever these two things are given, propagation delay, if your propagation delay questions, okay, propagation delay questions, if you have, then the best way is what? What is the best way? The best way is timing diagram. Okay, just make timing diagram. So you can easily solve this question with the help of timing diagram. Okay, let me make the timing diagram. Okay, so let me make it. So x is already 0, y is already 0, so you don't have to worry about it. Okay, I can simply say x is 0, y is 0. Just focus on z. What is z? Okay, now let's make the waveform for the z. So what I will do to check all the options, you can see options are saying z is going from 1 to 0, z is going from 0 to 1. So to check all the options, what I will do, I will make this type of waveform. See, look at this. I will make this type of waveform, so that I can check all the options. Okay, all the options I want to check. So let me make this type of waveform. Okay, this is the z. Remember, x is already 0, y is already 0, that is already given to you. X is 0, y is 0. Okay, so first what I will do, I will make waveform for A. Let's call it A. Okay, so what will be the waveform for A? There is a propagation delay. So tell me what will be the waveform for A? For A. A means there is a OR gate here. Okay, so you can see x is already 0. X is constantly 0. X is constantly 0. X is not changing. X is not changing. X is unchanged. Okay, so for x you don't have to create the waveform because x is already unchanged. Okay, so you don't have to create waveform for x. So tell me what will be A? What will be A? A will be xz. Yes or no? A will be xz. Right? Correct or not? Sorry, x or z. A will be x or z. And remember, A will be x or z, but x is 0. So A will be basically z. A will be same as z, but there is a propagation delay. Remember, A will be same as z, but there will be propagation delay. This will actually be same as z, but there will be a propagation delay. There is a propagation delay. This OR gate has a propagation delay. Okay, so what waveform you will get? Let's see the waveform. there is a propagation delay. So what waveform you are going to get? A is same as Z. So the same waveform you will get, the same waveform you will get, but there is a propagation delay. So what will happen? It will happen like this. The value of A is same as the value of Z, but there is a propagation delay. So what will happen? When the Z is changing, then when the Z is changing, notice when this input Z is changing, then remember the output of the OR gate will change after some time, after the propagation delay. This input Z is changing, but you can see the output of this OR gate, that will change after propagation delay. This is the meaning of propagation delay. Okay, because output will change after the propagation delay. When the input is changing, when this input is changing, this Z is changing, then output of this OR gate, that will change after the propagation delay. Okay, so this is what will happen. So you can see this waveform will be same as the waveform for Z, but you can see when Z is changing, then this output of OR gate, I can say this output of OR gate, that is A, this will change after the propagation delay. So you can see this will change after the propagation delay. Okay, like this. Similarly here also Z is changing. So the output of OR gate means this A, this will change after the propagation delay. Okay, and so on. Again you can notice that this Z is changing. So the output of OR gate means this A, this will change after the propagation delay. So like this, I hope you understood. So like this you will get the waveform. This is the waveform for A. Okay. Now what about this B? Let's call it B. The output of inverter. The output of inverter. What is B? Remember B is basically Z bar. Okay, B is Z bar. Yes or no? B is basically Z bar. Again there is a propagation delay. There is a propagation delay delta. Okay, you have a propagation delay. So remember, when the input Z will change, this input Z will change, then this output will change after the propagation delay. The input can change anytime, but the output will change after the propagation delay. Okay, so you can see here what will be the waveform for B. Let me make it waveform for B. So B is basically Z complement. B is basically Z complement. Okay, B is same as Z complement. Now let's see the waveform. What will be waveform? So this B will be the complement of Z. If Z is 0, B will be actually 1. Yes or no? If Z is 0, B will be 1. Remember, when Z is changing, then output will change after some time, after the propagation delay. Output will change. So you can see Z is becoming 1. Z is becoming 1. So this B will become 0, but after the propagation delay, this will become 0. This will become 0, but after the propagation delay. Okay, like this. After the propagation delay, this will become 0. Now similarly, you can notice this Z is becoming 0. So this B will become 1, but after the propagation delay. You can see this Z is changing here. But this output B, this output of inverter, this B, this will change after the propagation delay. Okay, after the propagation delay. And remember, all the logic gates have the same propagation delay. All the logic gates, they have the same propagation delay, right? Again, you can notice Z is changing. So this B will change after the propagation delay. Okay, this B will change after the propagation delay. So like this. Again, this Z is changing. So this B will change after the propagation delay. So like this. Okay, I hope all these points are clear. All the logic gates have the same propagation delay, right? Yes or no? So very simple. This is the waveform for A, B. What else we need? What else we need? Now we need to create the waveform for C. Let's call it C. Let me call this C. What is C? Can anyone tell me what is C? C is basically B or Y. Yes or no? C is B or Y. B or Y. But remember, Y is unchanged. This Y is unchanged. Y is static. Y is static. Y is unchanged. So you don't have to worry about Y. Okay, Y is basically unchanged. So C is same as B. C is same as B. Yes or no? C will be same as B. But remember, there is a OR gate here. So because of this OR gate, what will happen? When the B is changing, then C will change after the propagation delay. Okay, so remember, please understand, this OR gate you have. For this OR gate, the input is B, Y. Y is constantly 0. Y is always 0. Y is unchanged. So you don't have to worry about Y. You can see C. This C will be equal to Y or B. But Y is 0. So C is equal to B. C will be same as B. Okay, this output of this OR gate C, this will be same as the input B. Now remember, this input can change anytime, but this output will change after the propagation delay. So this waveform of C will be same as the waveform of B, but whenever B is changing, then C will change after the propagation delay. So this is the point. Okay, so remember C equal to B, C equal to B, but whenever B is changing, then C will change after the propagation delay. This is the point. Okay, so let's see here. Now let's see the waveform for C. Remember, C is same as B. C will be same as B. Okay, this is C, this is same as B. Now this will be same as B, but when B is changing, then C will change after the propagation delay. Okay, so the waveform will be like this. This C is same as B, C is same as B, but when B is changing, you can notice here B is changing, here B is changing. So the C will change after the propagation delay. Okay, so like this. Again, C is same as B, C is the same as B, but when B is changing, here B is changing, so the C will change after the propagation delay. Okay, again, here B is changing, so the C will change, but after the propagation delay. Okay, yes or no? Next, here B is changing, so the C will change, but after the propagation delay. So you can notice C and B, they are same. This B waveform, this is same as C waveform, but there is a propagation delay difference. There is a difference of the propagation delay. It's like this waveform has shifted. Yes or no? It's like this. For example, you can notice this waveform, they are same. But what is happening? I can say when you shift this waveform by propagation delay, then you will get this waveform. Okay, so anyway, this is simple idea. Finally, what the output P? Let's see output P. Let me see this. Output P is same as AC. What is output C? Output P, that is same as AC. Okay, AC. This is your output P. So now let's create the waveform for output P. How that will look like? How that will look like? Remember P, that is same as AC. That is same as AC. This P is going to be same as AC, right? Okay, so let's do A and C. A and C. Okay, so you can see A is 0, C is 1, so P will be initially 0. So there is nothing here, P is 0. Okay, there is no problem, P is 0. So you can see P is 0. Now you can see that at this point, A is changing. Okay, at this point you can notice A is changing. Okay, A is changing. You can see during this duration, notice during this duration. Okay, please focus on this duration. In this duration, what will be the value of P? Just focus on this duration. Please understand. Just focus on this duration. In this duration, what is the value of P? What will be the value of P? The value of P in this duration, A is 1, C is 1. In this duration, the value of P will become 1, right? And this is the glitch. Because actually P should remain 0. Yes or no? You already know. You already know that P should remain 0. The output should remain 0. The output should remain 0, right? But there is a glitch. What is the glitch? The glitch is here. Okay, just focus on the glitch. Let me show you the glitch. Okay, notice. Let me draw the glitch here. So the glitch is here in this duration. Notice in this duration. Notice here in this duration. Notice in this duration where A is 1 and you can notice C is also 1. Okay, in this duration. So please focus on this duration. In this duration, what is happening? In this duration, you can notice that A is 1, C is 1. So the output will become 1, right? And this is the glitch. Is this clear? This is the glitch. So tell me when this glitch is coming. So there will be a glitch here. Yes or no? P is becoming 1. This is the glitch. Okay, this is the glitch. So when this glitch is coming? This glitch is coming when this Z is going from 0 to 1. Okay, this glitch is coming. This is the output P. This is the output P. This should remain 0. But for a moment, this is becoming 1. When this is becoming 1, when this glitch is coming, this glitch happens when when this z is going from 0 to 1? Yes or no? When this z is going from 0 to 1. Okay, when this z changes from 0 to 1. So in this situation, this glitch is happening, and the glitch is like this. The glitch is like this. The value of p is going to 1. Okay, the glitch is like this. What is the glitch? The glitch is like this, that you must be 0, but for a moment you are becoming 1. Okay, this is the glitch. So your answer will be what for this question? For this question, what will be the answer? You can see the answer will be, when z is going from 0 to 1, then there is a glitch, and the glitch is that output is going from 0 to 1. So the answer will be option C. Is this clear? The answer will be option C. When z is going from 0 to 1, then output is going from 0 to 1. This is the glitch. For a moment, this is going from 0 to 1. I hope you understood. So the answer will be option C. Actually, you can easily notice here. Let me draw completely. Let me draw the complete waveform. So you can see the output, this P, this should remain 0, right? Yes or no? This should remain 0. Okay, this should remain 0. So you can easily see that this should remain 0. So far there is no problem. But when they are both becoming 1, okay, during this period, here A is also becoming 1, and here C is also becoming 1. When they both are becoming 1 in this period, you notice here C is also becoming 1 and A is also becoming 1. So what will happen? So P will become 1. Yes or no? You can notice A is becoming 1 here and C is becoming 1 here. So this output will become 1. The output will change, but after the propagation delay. The output will change, but after the propagation delay. After the propagation delay, output will change. Okay, the output will change after the propagation delay. So you can see this P will change after the propagation delay. This P will become 1. Okay. Now after that, again you can see this C is 0. So now what will happen? After the propagation delay, this will again become 0. Okay, because you can see now C is 0. Okay, now you can notice here C is 0, right? Here C is 0. So after the propagation delay, again this P will again become 0. Again this P will become 0. Until the next time. Again you can see, look at this period. Again look at this period. Okay, in this period you can notice A is 1. Okay, in this period you look at A is 1, C is 1. So again what will happen? This output will go like this. When both are 1, then output will change to 1, but after the propagation delay. Okay, so the output will change to 1, but after the propagation delay, the output will change to 1. Okay, but again you can notice C is becoming 0. So output will change to 0 again. After the propagation delay, output will change to 0 again. After the propagation delay, the output will change to 0 again. Okay, so like this it will happen. I hope you understood. Is this point clear to everyone? So you can see these are the glitches. These are momentarily glitches. Okay, you can see these are momentarily glitches. These things are happening momentarily. Okay, so these are the glitches. I hope you understood. So this is your complete question. So please tell me, understood this? The answer will be option C. Yes or no? So this is a beautiful question. This question I have taken from Cambridge University. Okay, very simple question. This is not a complicated question. This type of questions have already come in the GATE exam. Okay, propagation delay circuit is given to you. Okay, and the propagation delay is given to you. So basically this type of questions, circuit plus propagation delay, this type of questions have come in the GATE exam already. Okay, so this is very simple question from the Cambridge University. Okay, let's move on now. I hope you understood this explanation. Now let's solve this question. This is another digital logic question. So you can see this circuit is already given to you. The question is asking, neglecting the delays due to the logic gates. So basically don't worry about the logic gates delay. So, or I can say the delay is basically 0. Okay, the propagation delay of logic gates, these are the logic gates here. The propagation delay of the logic gates is 0. You neglect the delays due to logic gates. The decimal equivalent of the binary sequence ABCD, there is A here. Okay, there is B here, there is C here, there is D here. You can see A we have, there is B, there is D, there is C. Okay, so the question is saying the decimal equivalent of binary sequence ABCD of the initial logic gates will not change with the clock. Okay, what the question is saying, read this. The decimal equivalent of binary sequence ABCD of initial logic gates which will not change with the clock. Basically, which sequence of ABCD will not change with the clock? Okay, this question, please read the question. The question is saying that which sequence of ABCD will not change. Okay, once you have something here, like let me call it K. Once you have something here, this will not change, this will again be K after the clock. This will not change, this will again be K, means unchanged. Okay, after the clock, you can see. So the question is saying which will not change with the clock. Okay, with the clock, in the next clock also the same value will happen. In the next clock also the same value. In the next clock also the same value. So this is the question. I hope you understood the question. The question is asking what sequence of ABCD you take such that if you apply the clock, then that will not change. Okay, that initial sequence of ABCD, that will not change. Okay, so this is the question. Now let's solve this. The question is actually very simple. Remember one thing, that whenever a sequential circuit is given to you, this is a sequential circuit. Here you have two D flip-flop. These are the D flip-flop. Now you can see here, whenever sequential circuit is given to you where you have these flip-flops you have, then what you do, just make the state table. Yes or no? Just make the state transition table you make for the flip-flops. Like you can see here you have two flip-flops you have. Okay, so you can see, let me call it D2 and let me call it D1. Okay, I am calling it D2, I am calling it D1. Okay, you can see. So here you can notice what is this D1. What is the D1? Let's write all the equations. Okay, let's write all the equations. What you can say about D1? This input D1. Okay, let me call it input D1. This is your D1. What is this D1? This will be same as the value D. Yes or no? This D1, this will be same as the value D. This value D. So D1 is same as D. That you already know. Okay, this is the first thing you got. What is the next thing we got? What is the next thing you can write? This is D2. D2 is same as what? Tell me. D2 is same as what? D2 is same as what? You can see D2 is same as Q1. Yes or no? You can notice this Q1. This is Q1. Okay, this is Q2. So you can see this Q1. Please focus here. This is Q1 and this is Q2. So this Q1 is basically same as D2. Yes or no? So this D2, this is same as Q1. Okay, and remember this C is also same as Q1. This output of this flip-flop, that is the C. You can see, see the diagram. The output of this flip-flop, that is C. Similarly, the output of this flip-flop, that is the input of this flip-flop. So I can say D2 is equal to Q1. Also C is equal to Q1. What else you got? What is A? Tell me what is A? What is A? A will be same as Q2 bar. Yes or no? The output of this flip-flop, you can see this Q2 bar. Okay, the complement output. The complement output of this flip-flop, that is your A. Okay, so your A, what that will be? A will be same as Q2 bar. A is same as Q2 bar. Okay, what else? What is the value of B? Tell me what is B? B is same as A. Yes or no? B, that is same as A bar. B is same as A bar because there is a NOR gate here. Okay, you can see. So B is same as A bar. B is same as A bar. And that is same as Q2. So B is same as Q2. Correct? B is same as Q2. Okay. Next, what is D? Now you tell me what is D. What is D? Now tell me what is D now. So the D will be equal to, that is XOR of B comma C. That is XOR of B comma C. Yes or no? So these are the things that we found out. Yes or no? From the given circuit. So you can see from given circuit, these we can easily calculate. Yes or no? From the given sequential circuit, these things you can easily calculate. Okay. Now this question is very simple. Just make this state transition table. Okay. Just make the state transition table, means from which state you are going to which state. Okay, remember there are only 2 D flip-flop. So your state will be what? The state of this circuit. The state of circuit. What is state of circuit? We have seen this in our sequence circuit lectures. What is state of circuit? That is the output flip-flop output combination. That is flip-flop output combination. Flip-flop output combination. Flip-flop output combination. How many flip-flop are there? Please understand state of the circuit. This circuit is given to you. This circuit is given to you. What is the state of circuit? State of circuit is flip-flop output combination. How many flip-flop are there? 2 flip-flop are there. So your circuit, your state will be what? State of circuit will be simply Q2, Q1. This will be the state of circuit. Yes or no? This will be the state of circuit. Q2, Q1. Because you have 2 flip-flop here. In this circuit, there are 2 flip-flop. State of circuit, that is nothing but flip-flop output combination. So you can see the state of circuit will be Q2, Q1. Now let's see how the state is changing. Okay, so let me make like this. This Q2, Q1. Okay. What will be the Q2 next? What will be Q2 next? What will be Q1 next? Okay, what will be Q2 next? What will be Q1 next? Okay, and you have ABCD. And you have ABCD. Now let's see. So in this diagram, here you can easily see your D1 that is same as D. We have already seen. This D1 that is same as D. D2 is the same as Q1. D2 is same as Q1. So all these things we have already found out. Now you tell me, what is Q1? What will be Q1? This is a D flip-flop, right? Yes or no? This is D flip-flop. So what will be Q1 next? Tell me, what will be Q1 next? Because this is a D1 flip-flop. So what will be Q1 next? Q1 next. I am asking what will be the Q1 next? Just tell me this point. See this D flip-flop. This is a D flip-flop. So what will be the next state of this flip-flop? What will be Q1 next? That will be same as current value of D1. Yes or no? That will be same as current value of D1. See, this is the D flip-flop that is given to you. Now I am asking, what is the next state of this D flip-flop? This is your D flip-flop. What is the next state of this D flip-flop? Next state. I am asking next state of this D flip-flop. That will be the same as current input of the D flip-flop. Okay, so that will be same as your current input of the D flip-flop. That is your D1. That is your D1. Okay. What will be Q2 next? What will be Q2 next? Tell me. What is going to be Q2 next? Means the next state of this D flip-flop. This is a D flip-flop. What is the next state of this D flip-flop? Tell me. That will be same as the current input of this D flip-flop, that is D2. Yes or no? So you can see for this D flip-flop, what will be the next state? The next state will be same as what is the current value of D2? What is the current value of D2? So you can easily see that your Q2 next, that will be D2. Okay, so remember Q2 next. This Q2 next will be same as your D2. Okay, so let me create here. Let me create here D2, D1. Okay, and these are your ABCD. Okay, now let's see everything. Now everything is fine. Okay, so let's see how the states will change. Let me start with 0, 0. Okay, so we will basically check how the states are changing. Okay, how the states are changing. Means from this state, you will go to which state? From this state, you will go to which state? Okay, so let's see how the states are changing. Notice, from this state, what will be the next state? From this state, what will be the next state? From this state, what will be the next state of the circuit? This is the state of the circuit. What is this Q2, Q1? This is the state of the circuit. Because what is the state of the circuit? You already know. State of the circuit, that is flip-flop output combination. You have 2 flip-flop. So the flip-flop output combination, that is Q2, Q1. That is the state of the circuit. Okay, so you can see. Now let's find out. So just focus on this now. For right now, just focus on this. Forget about the remaining ones. Okay, right now, forget about the remaining ones. You just focus on this 0, 0 and you tell me what will happen now. Okay, what will happen? So if you have 0, 0, Q2, Q1, if they are 0, 0, then what is the value of A? Just tell me value of ABCD. Q2, Q1 are 0, 0. Q2, Q1 are 0, 0. What is the value of ABCD? What is the value of ABCD? A is Q2 bar. A is a Q2 bar. A is Q2 bar. So A will be 1. Because A is Q2 bar. Yes or no? What is A? A is a Q2 bar. Q2 bar. What is B? B is same as Q2. B is same as Q2. B is same as Q2. Okay, so this B, that is same as Q2. So your B will be same as Q2. What will be C? You can see C is same as Q1. C is the same as Q1. This is same as Q1. So that also will be 0. Okay. What about D? What about D? D is same as B XOR C. What is D? D is B XOR C. This D, look at this D. This D is B XOR C. B XOR C. Okay. So you can see if you do B XOR C, that will be basically 0. Okay. So you can see this is your ABCD here. What will be D2 D1? What will be D2 D1? You can see D2 D1. D2 D1 is same as D. D1 is the same as D. That is same as D. D1, that is same as D. Okay, so this D1 will be same as D. That will be 0. What is D2? D2 will be same as Q1. D2 will be same as Q1. Okay, so you can see D2, that is same as this Q1. So this will be 0. Okay. Now you can see what will be Q2 next, Q1 next. So Q2 next is D1. Q2 next is D2. Okay, Q1 next, that is D1. And Q2 next is D2. So Q1 next, that is D1. So that will be 0. And Q2 next, that will be D2. That will be 0. Now, that's it. You can stop now. Why you can stop now? Tell me. Actually, you can stop here. Did you notice one thing, that if you are in state 0, 0, you will again go to state 0, 0. Did you notice that if you are in state 0, 0, okay, Q2, Q1, if you are in state 0, 0, then again you will go to state 0, 0. Again you are going to state 0, 0 after every clock pulse. Yes or no? After every clock you are going to 0, 0. It's like you are in 0, 0. After one clock pulse, again you will go to 0, 0. After the next clock pulse, again you are going to 0, 0. So you are not changing the state. Yes or no? Yes or no? So your answer will be what? The question is asking what combination of ABCD such that the state is not changing. What combination of ABCD such that state is not changing? Read the question. What the question is asking? The question is asking the decimal equivalent of binary sequence ABCD of initial logic states which will not change with the clock. Okay, which will not change with the clock. See, here you can notice what is happening, that now the state will not change. Yes or no? Now the state is not going to change. Agree with me? So very simple point. If your state is 0, 0, then you will again go to 0, 0. You will again go to 0, 0. So your state is not changing. After every clock pulse, your state is not changing. So your answer will be what? What is the decimal value of this? The decimal value of this, that will be 8. So the answer will be 8. Is this understood? Please tell me. Is this clear? Let me know. Do you have any doubt? See, very simple. Circuit is given to you. In this circuit, the question is asking the decimal equivalent of binary sequence of initial logic states which will not change with the clock. Which will not change with the clock. Okay, so easily you can do this. First, what you need to do? First, you find out everything in this diagram. First, you find out everything. For example, you can see what is A. First, you find out everything. What is A? A is basically your Q2 bar. A is basically your Q2 bar. Notice what is B. B is same as A bar. That is same as Q2. Notice what is C. Notice what is C. That is your Q1. Notice what is C. That is your Q1. Notice what is D. That is XOR. What is D? That is A XOR B. Okay. Next, you can notice what is this D2. This D2. You can notice this D2. That is same as Q1. And notice what is this D1. This D1 is same as D. Okay. And similarly, you can see these are the D flip-flops. So what will be Q next? Q1 next. What will be the next state of this D flip-flop? The next state of this D flip-flop will be the value of D1. Okay. Similarly, what is the Q2 next? The next state of this D flip-flop. The next state of D flip-flop, this will be current value of D2. Current value of D2. So basically all these things you can find, these things you can find, these things you can find, and then you can solve this question easily. Okay, all these things you can easily find, yes or no? All these things you can easily find. After that, what you can do? After that, after finding all these things, all these equations you can find, after that what you can do? Just check if you are in this state, then what will be the next state? Okay, just make the state transition diagram, or I can say state transition table. just make the state transition table. If you are in this state, then what will be the next state? Okay, like that. So easily you can solve it. You can see if you are in this state, then the next state also will be the same, because from this state you are again going to the same state after every clock pulse. Okay, after every clock pulse you are again going to the same state. So your final answer will be, what is the decimal value of ABCD? The question is asking what is the decimal value of ABCD such that it will not change with the clock. So the answer is 8. Is this clear? So for this question, the answer 8. I hope this question is clear to everyone. Anyone has any doubt in this? Let me know. Do you have any doubt in this? Let me give you the complete analysis also. Let's see what will happen from this state. From this state, where you will go? Let's see that. From this state, where are you going to go? If you are in this state, you can notice from this state where you will go. Just check it. So you can see what is the value of A. The A is same as Q2 bar. So A will be 1. B is same as Q2. C is same as Q1. D is same as B XOR C. Yes or no? This D is same as B XOR C. So that will be 1. Okay. Now you just calculate. Just check it out. Okay. Just fill it. Basically, fill it. Fill this table. From this state where you will go. Just try to complete it. Okay. For your practice, just try to complete this. So try to complete this. Now you can see ABCD we have found. What is D1? D1 is same as D. D1 is same as D. So D1 is same as D. Next, what is D2? D2 is same as Q1. D2 is same as Q1. So that is 1. So you can see what will be the next state? Q2 next. That will be same as D2. And Q1 next. That will be same as D1. So you can see the next state will be 1, 1. Yes or no? Now from this state where you will go? Can anyone tell me? From this state where you will go? From this state where are you going to go? What will be the next state? If this is your current state, what will be your next state? This is what I'm asking. Okay, so let's see. Now you can see A is Q2 bar. So A will be 0. B is same as Q2. So B will be 1. C is same as Q1. So that will be 0. D is B XOR C. That will be 1. Yes or no? Now what will be D1? D1 is same as D. So that will be 1. Here you will put 1. What is D2? D2 is same as Q1. So that will be 0. Now you can see Q2 next, Q1 next. That will be simply 0, 1. So you will go to 0, 1. So if you are in this state, the next state will be 0, 1. Okay, finally, from this state, what will be the next state? If your current state is this, then what will be the next state? So again you can notice A is Q2 bar. A is same as Q2 bar. B is same as Q2. C is same as Q1. And D is B XOR C. So that will be 0. Okay, so you can easily notice here. D1 is D. D. So that will be 0. D2 is Q1. So that will be 1. So the next state will be 1, 0. Okay, now you can easily make the transition diagram. If the question is asking transition diagram, so you can see from 0, 0 you are going to 0, 0. You can see from 0, 0 you are going to 0, 0. Next, Q2, Q1. From 0, 1 where are you going? From 0, 1 you are going to 1, 1. You are going to this state. From 1, 1 where are you going? From 1, 1 you are going to 1, 0. So you are going to this state. And from 1, 0 where are you going? From 1, 0 you are going to 0, 1. Okay, so you are going to this state. So like this. This is your state transition diagram. State transition diagram. This is the state transition diagram. Yes or no? Is this clear? Please tell me. Okay. One more thing you can notice. If you are in this situation, means ABCD, if the ABCD value is this, then in the next cycle, what will be ABCD value? Just tell me. If your ABCD value is this, then in the next cycle, what will be the ABCD value? See, very simple question I am asking. If your initial ABCD value is this, then in the next cycle, what will be the ABCD value? Okay, let's focus on the ABCD. If your ABCD value is this 1011, if this is the ABCD value, then in the next cycle, the ABCD value will be what? Let me know. You can easily see in the next cycle, the ABCD value will be actually 0110, because if you are in this state, then this is the ABCD value. After the clock, you will go to this state, so the ABCD value will be 0110. Is this clear? Okay, so you can see after the clock pulse, what will happen? After the clock pulse, what will happen? The ABCD value, what that will become? That will become 0110. So is this changing or not? This ABCD value, is this changing or not? Yes, it is changing. Did you understand? See, very simple. If this is your current ABCD value, it means your current state is 01. In this state, your ABCD value will be 1011. Okay, so after the clock pulse, the next state will be 11. The next state will be 11. So the next ABCD value will be 0110. Yes or no? Okay. Now similarly, you tell me, if this is your current value, ABCD 0110, if this is your current value, after the clock pulse, what will be the ABCD value? What will be the ABCD value after the clock pulse? So you can see, if this is your current ABCD value, means this is your current state. If you are in this state, then ABCD value will be this. After the clock pulse, the next state will be 10, the next state will be 10. So your next ABCD value will be 0101. Next ABCD value will be 0101. You can see ABCD value changing or not? ABCD value, that is changing, and from here ABCD value is changing, right? But you can notice, you can notice, if your ABCD value is 1000, okay, if your ABCD value is 1000, notice here, if this is your ABCD value, then what it means? If this is your ABCD value, it means your current state is 00. If you are in this state, then ABCD value will be 1000. After the clock pulse, what will happen? After the clock pulse also, you will go to the same state, so the same ABCD value will happen. Yes or no? Did you understand? If you are in this state, then ABCD value is this. Okay. After the clock pulse, the next state is also same. The next state is also same. So the ABCD value will also remain same. So the ABCD value will not change. Yes or no? So after the next clock pulse, the ABCD value is not changing, right? And this is what the question is asking. The question is asking the ABCD value such that after the clock pulse, it will not change. This is what the question is asking. The question is asking ABCD value such that after the clock pulse, value will not change. So your answer will be 8. Okay, your answer will be 8. Correct? Is this clear? The question is asking what is the ABCD value? What is the ABCD value such that after the clock pulse, this value will not change. So your answer will be 8. Okay, so quite easily you can do this. I hope you understood. Okay, so this was another digital logic question. So did you understand? The answer is 8. This is a beautiful question. In this question, basically you can see your knowledge of everything you can apply. Okay, your knowledge of XOR gate is required, your knowledge of NOR gate is required, your knowledge of flip-flop is required. Okay, your knowledge of every concept of digital logic you need to solve this question. Okay, but this is actually very simple question. You can easily see in just you find all these equations, all these relationship. After finding all these relationship, you can easily see that, okay, in one line you can get the answer. Okay, just notice from this state where you will go. Basically just create the state transition table. Means if your current state is this, then what will be your next state? If you make the state transition table, you will easily find out that your answer will be 8. Because if your current state is this, then the next state is also this. Means if your ABCD value is this, then after the clock pulse, in the next clock cycle, the same value will happen. The ABCD value will not change. So that is the reason answer is 8. Okay, so this is a very simple question. Now let's move on. Now let's solve DBMS questions. Let's start with this question. This is a tricky question, let me tell you. And the video solution I have already provided. Okay, so you can see detailed video solution is already provided to you. You can just check it out. Okay, just click on this question, go to the answer. You can see under this question you can see easily that this video solution you can find. Okay, or what you can do, on the Go Classes YouTube channel you can find this video, tricky question on 2NF. Okay, on the Go Classes YouTube channel, you go there and you can find this video, or you can search on the YouTube. On the YouTube you can search tricky question on 2NF. Okay, this question you can search. Remember, let me tell you, this is actually a tricky question. You should search it and you should watch this video solution. Either you can watch this video solution from here, or you can watch this video solution on the Go Classes YouTube channel by searching this title, tricky question of 2NF. Okay, so you can just check it out. You can see here there is a student here who is saying that I did the same mistake today. The same mistake, because this is a tricky question. So this student is saying I made the same mistake today. Thank God I came to know about this. I would have done this same mistake in the GATE exam also. This same mistake I would have done in the GATE exam also. Thank you, sir, for giving this similar question in the All India mock test. Okay, so you can just check it out. Now let's move on. Let's solve this question. This question is from the transaction and concurrency. So let's solve it. You can see these schedules are given to you. Total 4 schedules are given to you. The question is asking which of the following statement are false. 4 statements, 4 options are given to you. Okay, the question is asking S1 is conflict serializable or not, S2 is recoverable or not, S3 is cascade-less or not, and S4 is conflict serializable or not. Okay, so let's solve it. Let's solve for conflict serializable. The question is asking this S1, this schedule, is this conflict serializable or not? For conflict serializability, what we do? If you want to check for conflict serializability, a schedule is given to you, this schedule is given to you, and if you want to check whether this schedule is conflict serializable or not, then what you will do? You will make the precedence graph. Yes or no? You will make the precedence graph. You can easily see. So this is what you are going to do. You will make the precedence graph. Notice here, a schedule is conflict serializable if the precedence graph is acyclic. Okay, so if you have a schedule and you want to check is this conflict serializable or not, then what you will do? Just make the precedence graph. This schedule will be conflict serializable if the precedence graph is acyclic. Okay, so let's make the precedence graph here. Let's make it. So what will be the precedence graph? How many transactions you have in this S1? There is T1, there is T2, there is T3. Three transactions are there. T1, T2, T3. 3 transactions you have. These are the transactions. Now let's see what are the conflict pairs. Let's see what are the conflict pairs. So you can see, is there any conflict? R1A, W2A. Yes, there will be A's from T1 to T2. There will be A's from T1 to T2. Okay, because you can see this is the conflict pair, right? Yes or no? So here you have the conflict pair. So you can see there will be A's from T1 to T2. Okay, what about anything else? From T1 to T3, do we have any A's? From T1 to T3. Yes, there is T1 to T3. Yes, there is A's from T1 to T3 also. Okay, you can see T1 is reading item A and T3 that is writing item A. So you can see from T2 to T3 there is A's. Okay, what else? What else? Let's look at this item. W2A. What will happen? Is there any A's? Let me know. Is there any conflict pair? Is there any conflict pair? So W2A to W3A. Yes. So 2 to 3 there is A's. Okay. What else? What about? So you don't have to check for T1 now. We have already checked for T1. From T1 to T2 and from T1 to T3 we already have A's. Okay. What about T2? From T2 do we have something else? From T2 do we have something else? T2 to T3 we have. Do we have something else from T2? Okay. Here you don't have to check. T1 is already done. What about T3? What about T3? Is there any conflict pair? See, this is read item of T3. So this is not a conflict pair. Okay, because remember here T3 is writing, T3 is reading. So this is not a conflict pair. This is not a conflict pair. Okay, because T3 is reading, T3 is writing, T3 is reading. So this is not a conflict pair. You can see there is no other conflict pair. Okay. So there is no other. You can just check it out. There is no other conflict pair. Yeah, that's it. So this is your precedence graph. Is this acyclic? Is there any cycle here? Yes, this is acyclic, right? So yes, this statement is actually true. The question is asking for false statement. This statement is actually true. The question is asking for false statement. So this will not be the answer. Okay, because this statement is actually true. This is actually true. The question is asking for false. Let's check for recoverable. When can I say a schedule is recoverable? When can I say a schedule is recoverable? Remember, the recoverable is like this. Recoverable. In which situation I can say a schedule is recoverable? Recoverable schedule. Okay. So the recoverable schedule is like this. This is your transaction T1. This is your transaction T2. If T1 is reading the item which is written by T1, see, if T1 is writing some item, T1, this is writing some item. If T2 is reading this change, okay, if T2 is reading the item which is written by T1, okay, basically T2 is reading from T1. What is happening? T2 is reading from T1. Okay. In this situation, recoverable, what recoverable says? Recoverable says that this T1 must commit before T2. Okay. So if T2 is reading from T1, then recoverable says that this T1 must commit before T2. Okay. This T1 must commit before T2. So this is the definition of recoverable schedule. Very simple. This is the idea of recoverable schedule. You can see, when can I say a schedule is recoverable? Schedule is recoverable if Tj reads an item written by Ti, then what should happen? What should happen? Ti must commit before Tj commits. Ti must commit before Tj commits. This is the definition of recoverable. So in this situation, the schedule will be recoverable. Okay, now let's see this. So here you have the S2. The question is asking for S2. In this S2, what is happening? There is transaction T1, there is transaction T2. In this S2, what is happening? You can notice T1 is reading item A, T2 is writing item B. Then what is happening? Then T1 is reading item B, then commit operation here and then commit operation here. Okay, this is the question. Now you can notice here, one thing you notice, that T1 is reading from T2. T1 is reading from T2, but T1 is committing before T2. So this is not recoverable. Okay, so I can say this S2 is not recoverable. This S2 is not recoverable. Okay, very simple, because T1 is reading from T2, but you can notice T1 is committing before T2. So this is not recoverable. So I can say this statement is actually false. This is a false statement. What about the next one? Next is cascade-less. What is the definition of cascade-less? What is the definition of cascade-less? Cascade-less says that you should not have any dirty read. There should be no dirty read. There should be no dirty read. Very simple. This is the definition of cascade-less. Means you should not have any dirty read. Means this is T1, this is T2. Okay. If let's assume T1 is writing some item A. Let's assume T1 is writing some item A. And let's assume T2 needs to read the item A. Okay, T2 want to read the item A. Then remember, cascade-less means that there should be no dirty read. You should not have any dirty read. Remember, T1 is writing item A. T2 want to read item A. Then what should happen? This T1 must commit or abort before T2 reads the item A. Okay, so you can see this commit should happen here, so that you have no dirty read. Okay, we have no dirty read. So very simple. Cascade-less means no dirty read. So let's check this S3. The question is asking this S3. Is this cascade-less or not? Do we have dirty read in this S3? Just check. Is there any dirty read in this S3? See, there is a read operation here. There is a read operation here. But this is not a dirty read, because T2 has already committed. T2 has already committed. So there is no dirty read. Notice here that T1 is reading item A. Then T2 is writing item B. T2 is writing item B, and then it is committing. Then it is committed. Then after that, this T1 is reading item B. Okay, then it is doing something. So you can easily notice that this is not a dirty read. This is not a dirty read. This is not dirty read because this T2 is writing item B and then it is committed also. You can see it is committed also before this read. Before this read operation, this has already committed. So I can say this statement, this is cascade-less, this statement is actually true. The question is asking for false statement. So this statement is actually true. What about the last? What about this last one? S4 is conflict serializable. Let's make the precedence graph for S4. For this S4, you can see there are only two transactions, T1, T2. Only two transactions are there. So this is the conflict pair. This is a conflict pair. So from T1 to T2, there is A's. Okay, what about T2 to T1? Yes, there is another conflict pair. There is another conflict pair. So there is like this. So it's like this. Let me tell you. You can see there is T2 to T1 and there is a T1 to T2 and T2 to T1, right? Yes or no? Because this is the conflict pair and there is another conflict pair here. So there is a cycle here. This is a cyclic graph. This is a cyclic precedence graph. So this statement has become false. Okay. Finally, what will be the correct answer? Finally, what is going to be the correct answer? So your answer, the question is asking for false statement. So which options are false? You can see option D is false. Option B is false, right? These are false. So the answer will be BD. The answer is going to be BD. Okay, so this is a very simple question. Now let's move on. Now let's solve this question. This question is actually a GATE exam question, let me tell you. You can see this is the GATE 2014 question. I have taken this question from GATE 2014 question, but small thing I have changed. See, this is a GATE exam question, GATE 2014. In this GATE exam question, actually they are asking whether this schedule is conflict serializable or not. Is this conflict serializable or not? Okay. Now, what I am asking? I am asking the number of directed edges. What is the number of directed edges in the precedence graph of this schedule? For this schedule, you make the precedence graph and you tell me how many directed edges are there in the precedence graph. The number of directed edges in the precedence graph. Now you might be thinking, what is the difference now? Actually, I want to tell you something, that this question many students they are solving with wrong way, with wrong method. Many students they solve this GATE exam question, this GATE 2014 question. Many students they solve using the wrong method, using the wrong method, using the misconceptions, using the wrong concepts. They solve this question. That is the reason I have created this question. The same GATE 2014 question I have taken and I am asking what is the number of directed edges in the precedence graph of this schedule. Okay, so let's make the precedence graph of this schedule. Let me make it. So you can see there are total 4 transactions, T1, T2, T3, T4, T1, T2, T3, T4. These are the 4 transactions. Now you can easily see. Let's see. First, let's see what are the conflict pair because of this. Because of this operation. With this operation, what are the conflict pairs? So you can see this is a conflict pair. Okay, what else? What else? Yeah, we have here. What else? What else? You can see. Yeah, that's it. Yes or no? That's it. You can see this is the read x, this is write x, this is write x. So I can say from T2 to T1, T3, from T2 to T1 and from T2 to T3. These are the edges you will get. Okay, what else? Let me tell you one mistake. Let me tell you one mistake. So the mistake that I want to tell you is like this. Some students, what they do, see this transaction has committed, right? This transaction has committed before this transaction started. This transaction started here. This T4 started here and T3 is already committed here. So some students, what they do, they don't make this type of edges in the precedence graph. Okay, they don't make this type of edges in the precedence graph. Let me tell you, that is a misconception. That is a wrong concept. Okay, actually this edge will also come. Means from T3 to T4, you will have this edge. From T3 to T4, there will be edge. From T3 to T4. What I am telling you, this is a misconception. What is the misconception? See, let me tell you a misconception, a major misconception. Let me tell you. This is a major misconception. What is this major misconception? And let me tell you, this misconception, this wrong concept is taught by some some faculties in other institutes, okay, some faculties on the YouTube also, they are teaching this wrong concept. You can easily find on the YouTube, you can find some, there are some very popular faculties, okay, very popular, millions of subscriber are there, I think lakhs of subscriber, okay, more than 5 or 6 lakh subscribers they have, and they are teaching a wrong concepts. Not only in the DBMS, this is not the only concept which they are teaching wrong. Actually, most of their content, let me tell you, I can say a major part of their content in all the subjects, that is actually a misconception. Okay, so these, I can say these faculties, these YouTubers, they have 5 lakhs, 6 lakhs, 7 lakhs subscriber. A lot of students, they follow these resources, but these are very poor resources. Let me tell you, these are very poor resources. They have 7 lakh, 6 lakh subscriber they have, but major part of their content, let me tell you, in all the subjects, major part of their content is misconception or wrong concepts or rote learning. Okay, it is full of misconception, it is full of rote learning. Okay, anyway, so let me tell you, this is a major misconception. What is that? See, major misconception like this, that if this transaction, let's assume this transaction has some wx and this is committed, okay, and let's assume there is another transaction which is starting here, okay, which is starting here. So you can see this transaction T2 is starting here, it is starting here, okay, and this T1 has already committed here, okay, T1 has already committed here, and this T2 is starting here, okay, T2 is starting here, you can see here T2 is starting, T2 starts here, okay. Now the misconception is, will you put this age in the precedence graph or not? Will you put this age in the precedence graph or not? Means from T1 to T2. Okay, remember this is also a conflict pair. See, if you say this is not conflict pair, if you say this is not conflict pair, then that is a misconception. If you say this is not conflict pair, then this is wrong. Okay, then this is a wrong. Is this clear? If you say this is not conflict pair, then that is wrong. Actually, the correct concept, let me tell you, the correct concept. Now let me tell you the correct concept. The correct concept is like this, that yes, this is a conflict pair. Yes, this is a conflict pair. Okay. The position of commit does not matter. When you check the conflict pair, remember the position of commit does not matter. Okay. So this is actually a conflict pair, and because of this, there will be age from T1 to T2 in the precedence graph. Okay, there will be age from T1 to T2 in the precedence graph. Actually, when you check this serializability, while checking serializability, let me tell you, the position of this commit does not matter. The position of commit, okay, the position of commit does not matter. Position of commit doesn't matter. Doesn't matter. Okay. Is there anyone here who has seen this misconception? This misconception, have you seen somewhere that, okay, if this transaction has committed and this new transaction is starting after some time, then we will not put this age. Okay, from T2 to T1, we will not put this age. Let me tell you, this is a misconception. This is wrong. Okay. So finally, let me tell you what will be the correct answer. So the correct answer will be, so you can see, okay, so you can see here, because of this, you will see there will be conflict pair here, there is conflict pair here, there is conflict pair here. Okay, from T3 to T1 also, from T3 to T1 also. Okay, from T3 to T1 also you have, and from T3 to T4 also you have, from T3 to T4 also you have. Okay, what else? This WX. So yes, there will be this also. So from T1 to T4 also, from T1 to T4 also, from T1 to T4 also, from T1 to T4 also. Okay, you will have age What else? What else? You can see WY, yes. So you can see this is also there. So from T2 to T4, from T2 to T4, yes, there will be like this. From T2 to T4, okay, from T2 to T4, and that's it. And that's it. Yes or no? So how many edges we got? 3, and so you can see how many edges we got. Tell me. These are the 3 and 3, 6. Total 6 edges we got. Yes or no? So total 6 edges we got. Is this clear? Please tell me. Anyone has any doubt in this? Let me know. So total 6 edges will be there. This is the correct answer. The six edges will be the correct answer. The 6 edges will be the correct answer. But if you have this misconception, okay, I told you this misconception, right? Yes or no? I told you this major misconception. If you have this misconception, or if you are following those, I can say, if you are following those faculties who teach these wrong concepts, if you are following them, then what answer you will get? If you have this misconception, then what answer you will get? Let me tell you. If you have this misconception, then you will get this type of answer. Let me tell you what type of answer you will get. So because of this misconception, what answer you will get? Let me just tell you that. Okay. So because of this misconception, you will do something like this. T1. Anyone want to tell me? Because of this misconception, if some student has this misconception, if some student is learning all these wrong concepts, then what answer they will get? See, then they will get this type of answer. Then they will make this. Okay, no problem. They will make this. They will also make this. T2 to T1 also they will make. So these things they will make. T2 to T1, T2 to T1 and T2 to T3. These they will make. Okay. But what they will not make, let me tell you. They will not make this. Actually, they will not make this. They will not make this. They will not make this. Okay, they will not make this. Okay, so they will not make this. And what else they will not make? They will not even make this. They will not make this also. And what else they will not make? They will not even make this also. So basically they will get only answer equal to 2. Okay, they will get answer equal to 2. Okay, 2 edges. They will get answer equal to 2. And this whole thing is nonsense, utter nonsense. Is this clear? This is nonsense. Okay, so this is what misconception does. Okay, so what you can do, let me tell you. If you want a proof, see, you might be thinking, sir, how can we believe you? Yes or no? You might be thinking, sir, how can we believe that you are right and those 6 lakhs, 7 lakhs subscribers, those faculties are wrong? Okay, if you want a proof, I have given the proof. Don't worry, I have already given the proof. What you do, you go to this GATE exam question. Okay, and for under this GATE exam question, you read my explanation. Okay, you read my answer there. You read my answer there. In my answer, I have already provided proof. I have already provided proof. Okay, so remember, what you can do, if you want, then what you can do, go to this question, this GATE exam question, you go on the GATE Overflow, on the GATE Overflow website, and you read my answer. I have provided the proof also. Okay, so don't have these kind of misconceptions. And very honestly, I want to tell you one thing, very honestly. The faculties who are teaching you all these wrong concepts, major part of their course, major part in all the subjects, major part of their content is wrong. Either it is wrong, full of misconceptions, or it is full of rote learning. Okay, so this is just a suggestion to you. You can decide yourself what to follow, what not to follow. Okay, anyway, so I hope this misconception is clear, right? Yes or no? Okay, let's see this question. In relational algebra, the join operator, this is natural join, is logically redundant if we have additionally which of them? Basically, the question is asking which of these operators, if you have, then this natural join will become redundant. Which of these operators, if you have, then you can implement the logical operator, sorry, this join operator you can implement using these operators. Okay, this is what the question is asking, that this join operator you can implement using which operator. Okay, so your answer will be, this is a very simple question, the answer will be option B, because what is natural join? See, what is natural join? Natural join, what will be that? If you have, for example, R natural join S, what that will be? R natural join S, what that will be? First you will do the cross product. This is the first thing you will do. Okay, yes or no? This is the first thing you will do. This is the first thing you will do. So first you will do the cross product. After doing the cross product, what you will do? What you will do? You will basically select only those tuples. You will select only those tuples where the common name attributes have same value. Okay, let me assume that R has ABC. Let's assume these are the attributes in R, and let's assume S has ABD. Now what you will do? First you will do R cross S. Then what you will do? You will make sure that only those tuples you will select where these same name attributes have same value. Okay, so you will select only those tuples. You will select only those tuples where these same name attributes in these two tables, in these two relations, the same name attributes, these same name attributes, they have the same value. Yes or no? So this is what you will do. They have same value, and you will also check that R dot B should be same as S dot B. After doing this, what you will do? After doing this, you will project only the unique attributes. Okay, only the unique attributes you will project, A, B, C, D. Okay, after this you will project only the unique attributes. Okay, only the unique attributes you will project, because here actually you will get total 6 attributes. Here actually you will get total 6 attributes, right? Okay, so what you will do? You will project only the unique attributes. Only the unique attributes you will project. So you can easily see the natural join, that is a sequence of 3 operations. First you do the cross product. In the cross product there will be 6 attributes. Then you select only those tuples where the same name attribute, they have same value. Okay, only select those tuples where same name attribute have same value. After that you project only the unique attributes. Okay, project only the unique attributes. So finally your answer will be option C. Okay, if you have these operators, you can easily implement the natural join. With the help of these operators you can easily implement natural join. So the answer will be option B. Okay, so this join operator, natural join, this is redundant, because you can implement this with the help of cross product, select, and project. Okay, let's solve this question. SQL usually treats a table not as a set but as a multi-set. This you already know, that SQL basically that will treat your table not as a set but as a multi-set. Means there can be duplicates. Means duplicate tuples are allowed in the SQL. Duplicate tuples can appear more than once in a table. Okay, also in the result of query. Is this clear? SQL, the input of SQL, also the output of SQL can have duplicate tuples. In the table you can have duplicate tuples. SQL does not automatically eliminate duplicate tuples. So this you already know, this is just a standard concept. Now consider two relations R, A, S, C. So two relations are given to you. Okay, and what this question is asking, that your table R is given to you, that is AA, BC. So in table R there are 6 tuples, because remember SQL allows duplicate, so duplicates are allowed in the SQL. Okay, similarly your table S, that has 6 tuples. Okay, duplicates are allowed in the SQL, duplicates are allowed. How many tuples will be there in the output of the following query? This query. Okay, how many tuples will be there? So very simple. From R, S, what that means? That is same as your cross product. You are doing the cross product. Don't eliminate the duplicates. Do not eliminate the duplicates, because SQL allows duplicates. Okay, so if you do R cross S, then how many tuples will be there? In R cross S, there will be total 36 tuples. And then you are basically selecting only the A, the attribute A. You are only projecting, you are only projecting the attribute A. Remember, SQL does not automatically eliminate the duplicate tuples. So if you project A, then again you will get 36 tuples in the output. Okay, you will get 36 tuples in the output. Now the same question, if they give you like this, select distinct. In the same question, if they give you this distinct keyword, okay, if they give you this distinct keyword in the same question, if they give you R, S, in the same question, if they give you this distinct keyword, now what will happen? Now duplicates will be removed. Now duplicates will be removed. If you have this, now the answer will be what? Now the answer is going to be what? That will be 3 only. Now the answer will be 3 only. Okay, because now the duplicates will be removed. Here the result will be A, B, C. Okay, the result will be A, B, C. This will be the result. So your answer will be 3 if you have this keyword, distinct keyword. Because of this keyword, what will happen? Duplicate tuples will be eliminated. But by default, duplicate tuples are not eliminated. Okay, so for this original question, the answer will be 36. Okay, so that is enough for today. I hope you understood all these things, all these questions, all the DBMS questions, all the digital logic questions. I hope you understood. Please tell me, did you understand everything that we have seen in this session? In this session, we have seen digital logic questions, also the DBMS questions of All India Mock Test 1. Please tell me, did you understand everything? The explanation of every question, did you understand? Did you learn something new? Please tell me, give me your feedback, okay? Give me your feedback, okay? So some more questions are remaining, like discrete mathematics. In the discrete mathematics, 3 or 4 questions are remaining. Also computer organization is remaining. So those we will discuss in the next session, okay? Discrete mathematics, some questions were remaining, right? Already we have taken 3 questions in the part 2. You can check it out. In the part 2 of AIMT solutions, we have taken 3 questions of discrete mathematics, but there are some questions which are remaining. So these we will take in the next session. Okay. Okay. Thank you, everyone. Okay. Thank you so much. So please share your feedback. Okay. After this session is over, if you are watching this session, please share your feedback. Please put a comment. Please like and comment. Okay. We are giving you detailed solution of every question we are providing to you. Okay. And definitely you will learn a lot of things you will learn. Okay. If you are thinking that speed is slow, then you can watch on 2x speed. Okay, you can watch at the speed 2x, but please provide your feedback. Okay, I'm very sure that this detailed explanation that we are providing to you, we are telling you everything in the question, what it means, what that means. Okay, what if this happens, what if that happens. We are telling you the variations also, and all these questions are standard questions. These are beautiful questions, and I'm also providing you detailed explanation of all these questions. So please share your feedback. Please put a comment. It will motivate us. If you are watching this video, please put a comment. Okay, so don't underestimate the comment power, so when you put a comment, we read it, we go through your comments. I and Sachin, we read all the comments on the Go Classes YouTube channel. Each and every comment we read. Okay, I personally read each and every comment. Okay, I also reply to many comments. So please put a comment. Please share your feedback. Whenever you are watching any video on the Go Classes YouTube channel, please like and please put a comment. Okay, you can put a small, big, basically just share your feedback, just share your review of that particular lecture. Okay, thank you everyone. Thank you so much.